So this exercise is about creating an interpretation of a map as illustrated on the cross section, and the map's got a series of faults. So let's look at a workflow for working efficiently through generating a cross section and then establishing the stratigraphic knowledge for the geology on the area. So let's take a look at the map and cross section together. We can see from the map that there's some valleys marked, which is where these rivers go up through the map like this. But otherwise there's no topographic information on the map at all. For that we have to refer to the profile down in this position here, and we can see that actually there's quite a lot of topography from 1,000 meters almost to 2,000, so that's almost a kilometer of topographic relief, climbing over the top here, down, over, down and back up. So this is relatively high ground. As we go along our section line here, another slightly high area in here, and then this position corresponds to this strange patch of rock over here. So we can use this information to draw the profile. Well, when tackling a map like this, I find it useful to put the faults on first. The faults should have the simplest geometry because they at least post-date the bedding and the stratigraphic units, which could be faulted and folded, so won't be as continuous the fault structures are on the map or on the cross section. Okay, so I've got a strip of paper here, just an offcut that I can use to lie out along the section line. There is the section point Y, here is the end point, just line it up there, which is X, and we'll just put the faults on where they occur. 1, 2, 3, 4, 5, and then this curious patch here, there and there. So those are the positions of the faults on our strip of paper. We just need to take this now and put it onto the profile below. So let's just line this up. Y is there, X is at the far end. Line it up like that. And now we can transfer these points onto our topographic profile. So I'll just use this device in here just to get them up properly. So there is where that fault exists. That fault down in the bottom of the valley there. That fault there. That one. That one. And these guys, oh look, just there and there, either side of that hilltop. So we've got our 1, 2 here, and then 1, 2, 3, 4, 5 faults that we recognised on the profile. Well, the next thing to do now is to get an idea of the dip orientation of these fault planes. And we can use this from the deflections they make into the rivers. So we can see that this fault plane here deflects and V's into this valley here, and this valley here, and this valley there, suggesting that it dips this way. And because the V is fairly pronounced, the dip presumably is fairly gentle down towards the left-hand side, the western end of the profile. So I'll just cartoon that on like this as our estimate of the orientation of this fault plane. Now let's continue to the next fault, which is this one here, which intersects our profile in this position. And we can see that this fault pretty much goes straight across these valleys, but if we look in detail, there's a slight deflection down towards the east in this position. So this suggests that the fault is not only quite steep, but dips this direction, so it V's a little bit into the valleys. So I'm going to interpret this fault here as dipping quite steeply down to the right, in other words towards the east. We can continue now with this fault here, which comes through, interesting because it looks like they intersect with this fault plane. But this fault again looks pretty steep, cut straight across the river here, maybe a little kink which might be that continuation of the valley. So I'm going to say this fault also dips steeply down towards the right, towards the east. Continuing a little bit further now, we can see that this fault plane Well, this one looks like it's another gently to the left dipping fault, because this V's remarkably into this valley in here. A little deflection on this one. So let's suggest that this fault is dipping towards the west, but at a moderate angle again, something like this. The next fault is this one in here. Looks like it's another one that's dipping steeply down towards the right, towards the east. Again, hardly deflects across the valleys, but where it does V a little bit, implying a easterly dip. So I'm going to put that fault in, and it's here on our profile, again quite steep. So now we come finally to these guys here. Well, this fault we can walk around here, so it makes a loop as a patch around the hillside. Well, if it links on the map, it must also link on the cross section. The next bit of information I can see is this fault doesn't cross the valley and go to deep. It's continually, essentially rimmed by these green rocks. So I'm going to suggest this fault is actually like this, so that the hilltop contains the rocks above the fault, which will be these guys in here, and the lower ground is the green, which we find on both sides of the hill, and indeed we can walk around, which is equivalent to walking underneath. So that's the pattern of faulting transposed from the map to the cross section. So that's part one of our exercise. Okay, well, I'll just remove the map strip now. Because what we need to do is to now part the geological formations onto here and see how they relate to the faults. And I'm going to start over here on the right hand or eastern side of the map. Okay, so let's get the other side of the map strip up so we don't get confused with our fault picks. Put Y on here, and I'm just going to put in some of the units. So there's the edge of this purple unit, there's the edge of the light blue. Just make sure that's all working. Just put the fault on again so we have it, and the fault, and then the other fault over here. Okay, I'll worry about what's going on in this position in a minute. I'm just going to put the rocks in that will plot beneath the fault plane. So let's just transfer that information onto the profile. There's Y. Okay, so the boundary here, which is this one, plots there. This one here, which is the edge of the green and blue, plots there. These are our two faults, fault, fault, fault. So that's all working quite nicely. So we've got two boundaries that we need to extrapolate into the subsurface. And for that, we're going to use the bedding readings. Well, I'm not going to obsess about precision here. I'm just going to point out the fact that these beds are dipping very gently down towards the west. So we can take these dip directions and just simply project them gently in to the west, out into the sky, and in doing so we're defining a thickness for this light blue unit in here, which we see from the key is called the black rock limestone. So this is the black rock limestone. This unit on top will be the Fairview limestone, and the cornfield limestone is underneath. Okay, so I'm just going to colour these in. Okay, so there we go. Now what happens as we take these rocks over to the other side of this patch, in other words here, and we can see the dips increase to what, 26, 28 degrees. So in this position the beds are dipping something like that. So if we take these down and project them down like this, then these beds are going to come over and gradually swing over something like that. And I'm just going to track these around to be parallel to one another. Here comes our black rock limestone around, and then finally the cornfield limestone. But we don't know where the base of that is. Well, I'm going to project that fault down and snap that horizon and that horizon onto the fault plane. And now we can colour that in. So there we go, just finish up with the cornfield limestone coming in underneath there. Don't know how deep it goes yet. I'll deal with that in a minute. We may get more information from elsewhere on the map. But what happens on this side of the fault? we got the eastern side. What happens over here on the other side, which is on the lower side, the footwall side of the fault? Well, for that we're going to take our map strip and collect the information from over here. Okay, so here we go. That was our fault that we got in before, and here we got the stratigraphic contact here, and there's the next fault. And put the other fault on as well, just so we've got it. So we've got these three units again: the Cornfield limestone, and the Black Rock limestone, and the Fairview limestone. And we can transfer that and put it onto our profile. Okay, off we go. Take that across, put it up here again. There's that fault, there it is at the outcrop. There's the other two faults, 1, 2. Just tighten it up. So there is the boundary, and there is the boundary in here. Just put little patches of colour on this so we know where we are. A little patch there of the blue, just to confirm that this is the Black Rock limestone. But what about the orientation of the bedding in here? Well, I can see that the bedding here, 22, 24, slightly more gentle, but still to the west compared to these units over on this side. So I'll just take that information and draw these on like this, which is interesting because it's more or less the same orientation as this fault that I inferred from before. Up to the fault, let's put this fault in here so we can snap that to the fault. Take this up higher still, and we'll snap that to the fault so we know what we're doing. And I'm trying to make sure that those dips are a bit steep, aren't they? Let's make them a bit more gentle. Like that. That's a bit more like it. Like this. And I'll colour that in so I know what I'm doing. That is the Black Rock limestone. There's our patch there of Cornfield. A little thin strip here of the Fairview just coming in. And we can see that sitting on top of this fault is this unit in here, which are gneisses. And that forms that hill. Well, let's add a little bit of structural interpretation already on this, and we can see that this fault dips down in this direction here, which is towards the east, and it down throws to the east like this. We'll show the fault offset with that arrow, tidy it up a bit. So that's a normal fault. The hanging walls move down, and we can correlate the Black Rock limestone, indeed, all three units, across the fault from footwall to hanging wall. But what about this fault here? Well, this, if I just draw it on like this, is a thrust fault because it's putting gneisses, metamorphic rocks, on top of sedimentary. So that's a thrust fault, but we don't know whether it's moved this way or that way yet. What's interesting though, let's return to this piece over here that we've ignored a little bit up until now. And we can see that above this fault on the map, we've also got gneisses, and indeed gneisses with Cornfield limestone sat adjacent to it, dipping off towards the east. So I'll just draw that on. Let's just capture that information, put my pencils down, and just capture the width of the fault patch in here, and that's where that boundary is. Take that across to our profile. There are the two fault picks. That's where that boundary is at outcrop. So I'm going to suggest that actually it comes down onto the fault plane. We can see that this boundary comes onto the fault plane here. So it's going to come down onto the fault plane pretty steeply because these rocks are dipping at 72. So we have that part of the section. Just colour that up. Gneisses on one side of this patch. And on the other side we have the Cornfield limestone. Like this. And a fault between, and this fault, which I'll just extend out, is another thrust fault, T, because it's putting gneisses on top of sedimentary rocks, but this time it's also carrying some other sedimentary rocks. These rocks, the Cornfield limestone, are lower on the section out here than the Fairview limestone, so this fault is putting the Cornfield limestone here on top of the Fairview limestone, so that's carrying deeper rocks up onto shallower. So again, it's behaving as a thrust. It's carrying metamorphic rocks and older rocks onto younger. Okay, so this is working pretty well for this part of the cross section. But now we're going to go over here, which is this part of the map. We can see there's far less variety of rock type along here. We've got lots of these gneisses in pink, and we've also got this tract between two patches of gneisses of the cornfield limestone. So what's the relationship between the cornfield limestone and the gneisses? Well, on the profile it's faulted, but if we come up to here, we can see that we have a contact, which is the unfaulted original contact between the cornfield limestone and the gneisses. That contact V's into the valley here, so in other words it's dipping off this way towards the west, and therefore the cornfield limestone is sitting stratigraphically on top of the gneisses, and the gneisses lie underneath. And that contact almost comes onto our fault plane in here. So what I'm going to propose is that in this position here, we've almost got gneisses coming up, and they're not quite in the section, dipping moderately gently down like this at a few degrees, coming down onto our profile, something like this. Okay, so we have our fault, we have gneisses, and then we have on top the cornfield limestone. So let's just colour that in. Like this, with gneisses underneath. Right, interesting. Now some decisions to be made about what's happening down in here. I'm going to keep pushing along. I'm also going to put in what's missing up in the sky here. If we come through this panel of cornfield limestone down to the southern end of the map, we can see the cornfield limestone is overlain by the black rock, which is the same relationship as we see here, and will be represented on our profile. So I'm going to suggest that at some elevation above, now eroded in our profile line, we would have had the black rock limestone, which here stratigraphically overlies the cornfield, but in our profile has been eroded away. So I'm just going to put a patch of it on here just so we can see what's happening, and I'll draw in the eroded part of the cornfield limestone as well. Okay, so a bit more of our profile drawn on. Let's continue across. I'm going to come in from X this time and put in this bit of geology. I'm going to measure from X because it introduces less measuring error than coming in all the way over from Y. So I'm going to put X on our profile in here. There is that fault. There is the boundary here. There's that boundary down to the gneisses, and just to make sure it's all tying up, there's the other fault. So I'll just label that fault, so we know where we are. Take it onto our profile down in here. Line it up with X. Let's just put it down like this. Try and tie it up with my set square so we get this about right. Sorry, that was X, wasn't it? Not a fault. That's X. That's the fault. That's the fault there. So that's the fault. That's X. That's right. There's the fault. So this is the position. If I just use my set square to tie that up, that's where that boundary comes in, which is the boundary between the black rock limestone and the cornfield. This one in here, which is in that position, which is this guy, onto the gneisses. So all this is gneisses. Again, we can be fairly straightforward with this. The dips are gently down towards the west, towards X, so they're coming down something like this. So there are our units. That's the fault carrying gneisses across. So let's just colour that in. So we've got gneisses here on top of the two limestone units, which in turn sit on gneisses. So two limestone units sitting in turn on gneisses. That presumably is the unconformity, a stratigraphic contact. It's equivalent to this one here that we see in this fault block, and indeed it's equivalent to this one here. So we see the unconformity onto gneisses in three different places on our profile. What about this fault here? Well, this fault inclined down in this direction is putting gneisses on sedimentary. I'm going to start labelling these up by putting a triangle, the conventional way of showing a thrust, and a triangle on the upper side of it to show that's the thrust fault. And we have it again here, as we saw, and we have it over here on this patch. Right, so how is this all going to work? We haven't finished our interpretation. All we've really done is compile the surface geology. We made a little bit of interpretation here into the subsurface, but otherwise that's not enough to understand what's going on. We need to make some further deductions. So I'm going to make an assumption here that there's one thrust, and this thrust is the same as this fault, is the same as this thrust fault here. So if that's the case, it means that this structure in here looks like it's been cut by this set of faults. So in other words, we've got a low angle thrust which originally went right over the top, and it's been chopped and down thrown by a series of faults in this orientation. Well, in fact, 3 faults in this orientation. So let's explore the consequences of that. Well, I'm going to draw this fault on here and suggest that these rocks, not surprisingly, originally came right over the top of this ground, because these overlie the gneisses, so therefore they originally would have been over here. And look, that explains how we have this package down in here down thrown. So again, let's just colour that bit of geometry in. Well, that makes it a bit clearer, but I've not quite finished this, because actually this thrust would have originally gone over the top of all this lot if it's going to connect with these guys. So it's come over to here and it's been cut by this fault. So let's just put our thrust fault geometry across. Well, if it does this, it means this thrust is going to be down thrown to somewhere about here, along with the rest of the stratigraphy. So this bit has been pushed down. And now let's put in this fault and then suggest, oh look, this might have also come down like this. Ah! Now we can match the thrust to here, and we can put the rest of the stratigraphy in. Like this. Well, there are a few unexplained relationships we've got to consider still. If we look at this fault here, on the hanging wall side, which is the east, we can see that we've got these green Fairview limestone rocks. But as I've drawn it so far, on the footwall side to the west, we've only got the black rock and cornfield, so there's no Fairview. So maybe the Fairview truncates backwards against the thrust fault in here. So we have a little patch of Fairview truncated by the thrust as you go back down towards the west. And these other units can come in like this, just draw the boundary on. Something like that. So now we can match across the normal fault the various units, the thrust sheet, the Fairview, the black rock and the cornfield limestone. Oh, and of course the gneisses that should be underneath, which actually will exist at depth down in here. And once we've got gneisses down in here, we can take this thickness of cornfield, draw it on in here, and even continue this all the way out to the front and say that just below Y we'd have gneisses at depth with our overlying purple cornfield limestone coming right through. So we're beginning to get a working cross section now. Finally, let's just snap that to the fault. So we say that this thrust has been offset down to here, offset down to here, offset down to here, but it's originally come from over here on the western side and run right over. So I'm going to suggest the movement of the thrust has been like this, coming right over to this position, carrying finally a little patch of the cover of the limestones on top. Otherwise gneisses that originally overran everything but been dropped down by a series of, or 3, down to the east normal faults. So now let's take our stratigraphy and just build our generalized vertical section. I'll use this piece in here just to measure up some thicknesses. That's a thrust, but as we go down we have these 3 units like this. Take those across and just hang that from there. That's that contact, that's that contact, that one there, and this is the top that we don't see. So here is the residual bit of the Fairview limestone, terminated by a thrust, chopped off or decapitated. The Black Rock limestone, the Cornfield limestone, and beneath the gneisses. So that is our stratigraphic order. It's a generalized vertical section showing more or less the true stratigraphic thicknesses of the unit, with the Cornfield limestone at depth, the Black Rock limestone, and then the Fairview limestone. So that is our stratigraphic order. The rock sequence here, this is just a key, it's not a rock sequence. So this is the true rock sequence shown on the generalized vertical section. So there is our cross-section drawn from the map. Our workflow involved putting the faults on first. This is because they have a simpler form than the stratigraphic units, which would have been there earliest and therefore have a more complicated and longer geological history than the faults themselves. By putting the faults on and then gradually building up one fault block to the next, we can tie the stratigraphy across and make sense of local geology and use this to help our understanding as we push our profile further on. Important to try and do this in places where there's the maximum information. In this case, where we had various units abutting the fault plane, rather than start down in here where there's many ways you could try and interpret this section. If you start in this area, you want to build from an area where you can get the most knowledge and move into the least certain parts of the section as you go. So a simple illustration of cross-section construction through faulted terrains.